This is our Play-Doh circuits formal lab. Motivation for this project was to understand how series and parallel circuits work together and how current and voltage are affected by different additions like resistors within it. This also allows us to understand how area length and resistance affect resistivity through a circuit. And our research question was, how do physical dimensions and the total resistance of a Play-Doh object relate to its material resistivity? Important things to know are voltage, which is the pressure or force that pushes electrons through a circuit, current, which is the rate at which electrons flow throughout a conductor, resistance, which is going against or opposing the flow of current in a circuit, and resistivity, which measures how strong a material opposes the flow of electric current. For procedure, we formed the Play-Doh resistor, set up the batteries, LED motor, and capacitor, and made sure that they were parallel to each other. We then changed the circuit until the LED was lighting up and the motor ran, and here are our materials. Independent variable was the shape of the resistor, while its resistance was the dependent, and our controlled variables were the Play-Doh, wires, voltage, and measuring tool.
The goal of this experiment was to create a working circuit with batteries, a Play-Doh resistor, an LED, a capacitor, and a motor fan, where the LED light and motor would both work simultaneously. Overall, we found that both the LED light and the motor would work when the LED was in series with the motor and resistor, meaning the current would stay roughly the same between the LED and motor resistor elements, with the voltage being the same between the motor and resistor since they are in parallel. We found that our resistance values from the pre-lab experiment and the experimental value we collected were not far off, with our pre-lab value predicting 1.3 ohms and our experimental value being 1.5. However, other experimental values of ours did not align. For our models and representations, we used physics ideas of conservation of charge, which kept the current through the node constant, conservation of energy, which kept the power consistent throughout the system, and Ohm's law, which is used to connect voltage change, current, and resistance. On the right, we have our circuit diagram to represent the experiment, which is shown in the photos on the design slides, which shows the LED that is in series with both the resistor and motor, while the resistor and motor are in parallel to one another. Continuing on the models we used, the power box on the left shows the voltage and current representations, which add up to the total power, with the LED being horizontal because it's in series, and the motor and resistor being vertical since they're in parallel. On the right, we have our system schema, which shows the force interactions between the different components of the circuit, with electric interactions between the battery and capacitor as well as throughout, and gravity between the earth and the circuit. Using Play-Doh, we molded our resistor into a lightning bolt, which had a length of 8.1 centimeters and an area of 13.5 square centimeters. The calculation for the area can be seen on the right.
This is the data from the pre-lab, so we used the resistivity value from the pre-lab in order to get the resistance of the Play-Doh resistor using the new length and cross-sectional area. So this is the equation for it. And we compared the resistance from the experiment with the resistance found here from the pre-lab with the new values. So as you can see, we got a value of 2.184 for the resistivity from the pre-lab with a new length and area, and we calculated to get a resistance of 1.3 ohms. This is the experimental data, and as you can see on the right, this shows a picture of the resistor and motor combined, and this shows that the LEDs in series with the resistor and motor, which are in parallel with each other. So what should have occurred was that the resistor and motor had the same voltage because they are in parallel, and as you can see for our data, they are not, with the resistor being very low in voltage, and the LED and motor / resistor should have the same current, which also isn't the case as the resistor, as I said, its current and the motor are too high.
This slide shows the calculations we used to arrive at the resistance and power values for each element in the circuit as represented in the experimental data table before.
This is our theoretical predicted data, and we use the new resistance of 1.3 ohms and the voltage of the battery, which is 2.93. And since our experimental values are incorrect, we use all the laws that we learned in class to change the values to the pattern it should be. So for uncertainty, this is the graph that we had in our pre-lab showing the length versus resistivity. It had a slope of 4,450 meters and a standard error of 1,433. And in the pre-lab, area was multiplied by the slope, which was the resistance over length, and a standard error value to produce the uncertainty of the resistance using the formula below. And as you can see on the bottom right, that shows the equation for finding the uncertainty for the resistivity in the pre-lab, which we got a value of 0.70. And the experimental data had no calculations for uncertainty, but we would use the same formula that we used in the pre-lab. So we had two things for the error. We had error reduction and sources of error. So for the sources of error, we found out the Play-Doh resistor was difficult to calculate for the surface area, and the multimeter was giving unsteady results in different measurements. And also the probes in the Play-Doh resistor had to keep getting pushed back because they would separate from the Play-Doh. And then for error reduction, we had quick measurements to avoid heating, repeated trials, consistent person, use less wires so we get a better measurement reading, and use a different shape so area is easier to understand. So for our overall conclusion in scientific reasoning, when looking at the circuit, we found that the motor and resistor were in parallel and the LED was in series with both of them. This signifies that our experimental data was incorrect because the voltage was not the same in parallel and the current was not the same when in series. The pre-lab resistance was similar to our experimental resistance, but it's kind of insignificant because the rest of our numbers did not make sense and did not follow the pattern. And we were successful to create a circuit with all the components, but we did not measure the current and voltage correctly in the experiment.